Alright. Cannot wait to get started.
Yeah.
Alright, so we have normal random variables to talk about today. Alright, so this is our last of our named random variables, at least for now. It's not quite true. We'll do some things with normal random variables and we'll see how things are tied together. But we will talk about normal random variables today, normal distributions. I'm going to skip over, I'll talk about some of the technical aspects, I'll skip over some of them for now. I want to get us to a point today so we at least know how to work with it, have some idea about what sorts of things it measures or it's trying to count, what x would be, and some things like that, so we can actually work with it. So, the normal distribution, unlike the other random variable, most of the time when we have a new random variable, I give some indication of where it comes from. We started with Bernoulli, that led to binomial, and of course, it also led to geometric, and then negative binomial, right? We sort of saw how all of those were tied together. Even hypergeometric was separate, but in some ways it was sort of similar. Poisson, we saw where that came from, and then we moved over to uniform. Well, we just threw uniform out there. Why not? It's uniform. It's simple. But then exponential, we motivated that using Poisson random variables. Even gamma, we motivated using Poisson random variables. So everything has pretty much been tied together. I'm not going to motivate this one right now because we just don't know enough to understand why this crazy function would at all be a good probability density function. Okay? It's not quite going to fit into anything else now, but later on it's going to fit into everything else. It's just hard to see why for the moment. So we'll skip over any sort of motivation for it. You've all heard of the bell curve or a normal random variable. It's the one that looks like that. If you're thinking of probability, maybe it's the first picture that ends up coming to mind. That's our normal random variable. Okay? It has a probability density function. So if x is my normal random variables, I have two parameters attached to every normal random variable. I have a mu, Greek letter mu, and I have this other Greek letter sigma squared. Okay. Now let me just say, depending on which book you're reading, when they talk about a normal random variable, they may use mu and sigma. This book used mu and sigma squared. A lot of books use mu and sigma squared. Honestly, if you're in a probability class, they'll probably use mu and sigma squared. If you're in a statistics class, they'll probably use mu and sigma. So that's sort of the difference. So just know which one you're working with, and we're working with sigma squared. So here's the probability density function. I wrote this down earlier because it's sort of tedious to have to keep rewriting this, but f sub x of x is equal to 1 over sigma square root of 2 pi. Okay. So this sigma is the square root of this number right here. E to the power of negative x minus mu quantity squared, and up in the exponent divided by 2 sigma squared. Now, first of all, take my word for it, that is a probability density. What would need to be true for that to be a probability density function? Is 1, yeah. It should be a positive function, which it is because it's an exponential function. This exponential function squared. So it's going to be greater than or equal to 0 everywhere, and then the area under the curve would equal 1. Take my word for it. Maybe on Monday or Friday of next week, we'll go through the argument as to why we can see why do we need the square root of 2 pi in there? Because we need the square root of 2 pi to make sure the area underneath the curve is equal to 1. Okay, but that's the idea. Okay. And I say we'll do it later because we cannot find an antiderivative function of this function. Okay. Which means we will not find any sort of nice cumulative distribution function for that random variable. Right? To find a cumulative distribution function, to compute probabilities using the fundamental theorem of calculus, we need to be able to find basically the antiderivative of e to the negative x squared, and it's not going to happen, right? It's not that it's hard, it's not possible to find the antiderivative function in a sort of nice way. Now, I could write out the Taylor series for this, right? E to the negative, and I could take the antiderivative of the Taylor series, sure. But I mean, when I say I can't find an antiderivative in any sort of nice way, you know, most of the time we take the antiderivative of an exponential function with something, it'd be an exponential function and I'd have some other terms there. There's just no way to write it as a composition of exponentials with polynomials or rational functions. You can't even throw in logs and inverse trig functions. You can't put those things together and find an antiderivative function. It is actually one of these functions. It's impossible to find a nice antiderivative function for this. Okay? Which makes things difficult for us because I compute probabilities by finding areas under the curves, and I find areas under the curves by using this fundamental theorem of calculus, part 2, which says take the antiderivative function, plug in the two endpoints, and that's what your area is. I can't do that, so that's going to be a problem. It's okay, we can overcome it. Let's see, for the moment, I'll just tell you that if I have a normal random variable, mu and sigma squared, the expected value is mu, and the variance is sigma squared. We're not going to justify that. You could actually pretty easily compute the expected value of that. It is difficult to find the antiderivative of e to the negative x squared. It is not difficult to find the antiderivative of x times e to the negative x squared. Right? What would I do there? Ds. Use substitution. Yeah, that's it. Right. So not having the x there, tough. Having the x there, not tough. X squared there, tough. Right? So just keep that in mind. So you could compute that expected value if you wanted to. If you worked really hard, you could figure out the variance. One more note here. Standard normal. So we're gonna tie everything back to what's called a standard normal random variable. When I talk about a standard normal random variable, I'm talking about the particular normal random variable or normal distribution where mu is equal to 0 and where sigma squared is equal to 1. So I'm talking about the particular normal random variable that has an expected value of 0 and it has a variance of 1. Okay. And if that's the case, right, and I plug a 0 in for mu and I plug a 1 in for sigma squared, then I would get this probability density function 1 over the square root of 2 pi times e to the negative, I guess I'm using a z there, z squared over 2, which is pretty difficult to deal with. Okay. So, all right. So every time I talk about standard normal, I'm talking about the particular normal random variable where the mean is equal to 1 or mu is equal to 1 and sigma squared, the variance is equal to, the mean is equal to 0 and the standard deviation, or the variance, the sigma squared, the sigma is equal to 1. Okay. All right, so we do have a difficult, if I want to compute the probability that I have, if I have a normal random variable like this, then I compute that using a definite integral with the probability density function. And I do that by using the fundamental theorem of calculus, using the cumulative distribution function, which is an antiderivative of the probability density function. And I'm telling you, we do not have a nice cumulative distribution function. We can't do it in the same way. And so typically, we're going to have to do this by some sort of numerical approximations. Right? I can approximate the area under the curve, right, by Simpson's rule, or the trapezoidal rule, right, or I guess the right-hand or left-hand rule, but something like Simpson's rule. Right? If you remember that, you approximate the area underneath the parabola. Instead, there's this formula. It has, 1, 4, 2, 4, 2. But anyone remember their Simpson's rule? It doesn't matter because we're not going to use Simpson's rule. Someone did it for us at one point. But I'd have to use some sort of numerical approximation. And we're going to see this, that what we're going to end up using are oftentimes what have been used are these table of values. And if you see a table like this for this says standard normal probabilities, this is a table that's actually telling me for the standard normal random variable down there on the left, how much area is to the left of a certain point. Okay. So this table is telling me what's happening for the standard normal random variable where mu is equal to 0, where sigma squared is equal to 1. And if I want to know how much area is to the left of 1, for instance, if I could read that, it's pretty fuzzy, I think it's 0.8413. So if I don't have a way to use the fundamental theorem of calculus with the cumulative distribution function, I need to approximate the area under the curves, something like that. The problem here is that every time I have a new normal random variable, right, a new normal distribution, I would need a new table, right? Every time I have a new mu, and every time I have a new sigma, I would need a new table like that one to tell me what the areas are and have to calculate them myself. That would be a problem. I need infinitely many tables to end up doing that. Okay. And so we're going to actually go back to what we talked about on, what's today? Wednesday on Monday, and we're going to talk about how we can take a normal random variable and we can do a linear transformation on any normal random variable, and we can turn it into a standard normal random variable. Okay. So that if I want to answer a probability question up here, I can translate it to a probability question down here, and then I only need one table. Actually, that table that was up there on the screen a second ago, one table to compute the probability, and then I can use my probability down here and I can translate it all back up again. Right? So if I can't do this, if I can't translate it down to some standard normal random variable, then I have to go ahead and come up with a brand new table every time I have new parameters. But the idea is I can translate it down. I only need one table. I'll translate everything down to that one table. I'll answer my question, and then I'll go back and I'll continue on with the problem. Okay. So that's what we'll do, right? And so that'll be the idea here, is that we'll do this linear transformation on a normal random variable, and what it will give me is a new normal random variable. Okay. So we talked about this last time, to some degree, right? We talked about the idea that if x is a random variable, right, let's just say x is any random variable. Okay, we talked about what we could do with a function of that random variable. And in particular, if x is a random variable, and if, let's say I know its probability density function, let's say that's its probability density function. And let's say I know its cumulative distribution function, at least know what it should be, capital F of that, right? We usually use the capital because it's a name type right there. Okay. The question would be, what is the probability density function of y? Okay. What's my F of y? Can I even figure out what it is? Okay. That's what we were talking about for the second half of the class last time. And the answer is, everything turns out really nice when we're dealing with a linear transformation. I'm trying to remember if we did an actual linear transformation last time. I think we didn't, right? Well, let's just go ahead and do that, right? Let's write down the probability density function for y, right? Knowing that we know the probability density function for x, right? Of course, we understand the probability cumulative distribution. It might be difficult to find, but certainly we know what it is, right? Or sort of how to find it in theory. Can I figure out what the probability density function for y is? Okay. And remember, when we answer this question, when I do a function of a random variable and I want to answer questions like this, I always have to start working with the cumulative distribution function, because that's the thing that's telling me probabilities. So I can't just say, oh, I know what f of y, I know what the probability density function is. I probably don't, and I don't have a way to get my hands on it strictly from x. sort of straightforward, but what I can do is I can figure out what the cumulative distribution function is for y. And then I'll just take the derivative of that function and it will give me the probability density function for y. Okay? So that's what we'll do, right? So if I have the cumulative distribution function for y, that would be the probability y is less than or equal to some little y, right? That's exactly what that means, the cumulative distribution function. So what do we do next? Now we'll do a substitution, right? What is y? I don't know much about y, but I know everything that I need to know about x. So let me just write in there ax plus b instead of y is less than or equal to y. So I have a cumulative distribution function. I'm just going to write it as the probability that it is. I'm going to do my transformation here, right? What y is written in terms of x because x is the thing I do know about. Okay? And now I'll simplify everything. So if I subtract b from both sides and I divide both sides by a, then I get x is less than or equal to y minus b divided by a. And let me just say, I just assumed something. Does anyone know what I assumed and I didn't state that I assumed? I mean, that could be a wrong, this could be incorrect statement if something isn't true. Does anyone?
A is greater than 0?
Yeah, a must be greater than 0. Otherwise, it would have switched the direction of that inequality. So I'm just going to assume for the time being, we could handle it if a was negative. But that's just saying that the slope is positive. It's just saying that if the x's come in a certain order, you know, the first, the second, and the third, then y will be in the second order. Otherwise, if it's negative, it could switch the order around, right? So, I mean, that's all we're saying there. Okay. So, again, we could handle it if a was less than 0. It wouldn't be a big deal. And then this is, let's see, the probability x is less than this is just the cumulative distribution function for x with y minus b over a plugged into it. So if I do this sort of linear transformation, I can write down the cumulative distribution function for y. It's just the cumulative distribution function for x with y minus b over a plugged into it. So if I want the probability density function for y, I'll just take the derivative of the cumulative distribution function for y, which I already know written in terms of the cumulative distribution function for x with y minus b over a plugged in. And that's just a chain rule, right? The chain rule, it'll just be the derivative of the cumulative distribution function for x with y minus b over a plugged back into it, multiplied by the derivative of the inside function. And what's the derivative of y minus b over a? With respect to y? 1 over a. Which, I also know the cumulative distribution function for x is just the probability density function for x. So it'd be probability density function for x, y minus b over a plugged into it, and I'm going to take the whole thing and I'm going to multiply by 1 over a. Obviously, I'm also assuming that a is not equal to 0. A is positive is what I've assumed. So what this is saying is, if I start with a random variable, any random variable, and I know its probability density function, and then I do this sort of linear transformation on an ax plus b, then I can write down pretty easily the probability density function for the transformed random variable, the new random variable. It's just going to be the old one with y minus b over a plugged into it, and I would take the whole thing and I'm going to multiply by 1 over a. Now, if it's not linear, then everything's more complicated than this, right? If this was a square here, so that was a square here, so that was a square here, then I would have to take the square root of each side, right? And then when I do the chain rule a little bit, right, that would mean that there is a square root here. And then later on, when I have to use the chain rule and take the derivative of the inside function, the derivative of the square root of y minus b over a is much more complicated than the derivative of y minus b over a, right? I wouldn't get a 1 over a out there. Okay. So this works out nicely exactly because this is a linear transformation. Okay. And this part in particular is simple. But if it was a square there, we could figure that out also, right? It would just take more work. We just can't come up with some general formula. Okay. So, a couple of things we're saying that this is saying if I have a random variable and I change it by this, I can write down the new cumulative probability density function. It is not true in general if I start with a particular random variable and I do a linear transformation, I get the same kind of random variable. Okay. If you start with an exponential random variable and you do this sort of linear transformation on it, don't expect to get another exponential random variable. Because every exponential random variable looks like that, and of course if I do a transformation, my new random variable might look like that, okay? But it always has to start at 0. So if b is equal to 0, then I'll get a new exponential random variable, but if b is not equal to 0, I won't get an exponential random variable. If you start with any uniform random variable and you do that sort of thing, you will get another uniform random variable. In general, we just can't expect that we always get the same type of random variable if we transform a certain type of random variable. Okay? Exponential is an example that wouldn't work. But you could show if b is equal to 0, you would get another exponential random variable. So here's my claim, and that's why I left this up here from last class, is that if I start with a normal random variable, right, I shouldn't expect this, but I can show that it's going to be true. If I start with a normal random variable with parameters mu and sigma squared, and I do this sort of linear transformation, I will get a new normal random variable with parameters a plus mu b and a squared sigma squared. Okay. Right. Again, I can't expect that when I do a transformation on a random variable, I always get exactly the same, or I get the same type of random variable. But what this seems to indicate is my claim, put a question mark here, we have to show this is true, then I'll get the same type of random variable. Okay. All right. So let's go ahead and do it. So my x is my normal random variable. So here's the most technical part of this. We have to chase around some things. So here's the probability density function for x. Okay. So according to what we did over there, we can now write the probability density function for y. It should be the probability density function for x, but instead of plugging x into it, I'm going to plug in y minus b divided by a, and then I'll multiply by 1 over a on the outside. Okay, so I would get something like, for this one, 1 over sigma square root of 2 pi, e to the power of negative, and now I don't want an x, I want y minus b divided by a, minus mu, and that whole thing squared, and then I'm going to divide by 2 sigma squared. And then I would take that whole thing, and I'd multiply by 1 over. I mean, we showed that this was going to be true. It doesn't matter what my probability density function was, that if I do this sort of transformation that I'm asking for, my new one is going to have this, and that's exactly what I did. And so now what I need to do is show that this is actually the probability density function for that one right there. If I can show this is the probability density function for that, then I can get rid of my question mark. Well, that's not too bad if I know how to know what I need to clean up. Right, this 1 over a could come over here with the sigma. So I'll put that as an a sigma square root of 2 pi. E to the negative, now I need to clean up this. And so I'm going to factor a 1 over a out of this part. And then I'm going to take that 1 over a and I'm going to pull it outside of the square. So it's going to come, that 1 over a is going to come out of here and it's going to come out of the whole thing as a 1 over a squared. You have a few days after this to make sure that all my algebra is correct. But what's going to happen is I'll get a y minus b minus a times mu squared if I pull out a A from this, I'll get that. And that A will come out here, 1 over A will come out here, and then I'll pull it out of the squared, and it'll end up in the denominator here with it as an A squared, 2A squared, sigma squared. All right, okay? And now let's go ahead and look at this. Let me write one more step here. This to me looks like A sigma, let's see, square root of 2 pi. Just put a parentheses around those. E to the negative, and I could write this as y minus b plus a mu, and take that whole thing squared, divided by 2, and I could write a squared sigma squared, well, I could write it as a squared sigma. And it's exactly what I was hoping it would be. I'll just go ahead and correct that. Right? Because, let's see, if I want to write down the cumulative, or the probability density function for this normal random variable, right, how would it be different? Well, instead of having a sigma here, I would have, well, the square root of a squared sigma squared, which would be a sigma, and that's exactly what I have there. Okay? I still have my square root of 2 pi, which doesn't depend on the parameter, so that's fine. Instead of having a mu here, I should have I should be subtracting off a set of mu, a mu plus b, and notice I have my y minus, I have my b plus mu, a mu, right? But b plus a mu is the same thing as a mu plus b. So I'm subtracting off that mean, right? And so in the parentheses there, I'm squaring the whole thing, and then I'm dividing by, instead of dividing by 2 sigma squared there, I should be dividing by 2 a squared sigma squared there, which is exactly what I'm doing. So yes, this is the cumulative distribution function, this is the probability density function for this normal random variable. Okay. What this just showed us is, if I start with any normal random variable, and then I do this transformation, right, I end up with a brand new normal random variable. And so now I want to relate everything back to my standard normal random variable. Okay. That way I can turn my probability question into one random variable, and if I need to, I could use one table that approximates one set of areas, and I don't have to do it every single time. Okay. So the particular random variable, this particular transformation I'm interested in, instead of using y, I'll use a z. It's pretty standard with standard normal random variables. Okay. I'll take my normal random variable, I'll subtract off mu, and I'll divide by sigma, which is the square root of sigma squared. Okay. I'll subtract off the mean, I'll divide by what's called the standard deviation, which is the square root of the variance. And if I do that, I'll now have a normal random variable whose mean is mu minus mu over sigma would be, mu minus mu is 0, right, over sigma, and whose standard deviation, whose sigma squared, the new one would be, let's see, I'll take that and how do things transfer as time goes, right? It will be, well, transformation says it will be 1 over sigma squared times sigma squared, which will end up being 1. So that's the idea. Right? So every time I do this transformation on a normal random variable, subtract off the mean, divide by the sigma, subtract off the mu, divide by the sigma, I get, bless you, what's called a normal random variable. And not just a normal, I get a standard normal random variable. Okay. So if I have a particular problem that has a particular mu and a particular sigma, I can always calculate probabilities by switching it back to standard normal. So example. Actually, I said, oh, this will be a good one to do. And then I looked and I don't always read the book before I, what the examples the book does. He actually does something very similar. So IQ. thinking, what actually has a normal distribution? Heights have normal distributions, you know, if you pick gender, within gender, but IQ is one of these that has a normal thing. If you pick someone at random from the population and you measure their IQ, right? X is a normal random variable. Their IQ is a normal random variable with mean with mu equal to 100 and standard deviation equal to 15 squared. I mean, yes, it's pretty ridiculous that we're using sigma squared as a parameter instead of sigma, so I'll just write it as 15 squared. That's how IQ tests are set up, to have an average of 100 and to have a sigma squared equal to 15 squared. So people do studies on such things. The average IQ of a math major in college, well actually, of a graduated math major in college, the ones who made it through. Anyone know what that is? Anyone have a guess, right? So if the average IQ is 100 and the standard deviation is 15, or the variance is 15 squared, anyone have a guess? We'll make a guess.
So around like 120.
120 is better guess. They said 105 in my last, or 107 in the last class. It was actually 130. Now this could, I mean, this could be complete nonsense because the average IQ of a PhD in math they have is much higher than that even still. And I don't believe that. I know. Anyway, this was a claim. Actually, there was only one major. No, actually, I think this is probably not too far off. I mean, I think it's reasonable in general. And this would be nationwide. One major was higher than that. Does anyone know what major would be higher than that on average? Physics, yep. Physics was 132, so a little bit higher. And actually, number 3, anyone guess what major would be number 3? Philosophy. So, anyway, there you go. Anyway, so here's my question. It's always nice to throw that in there. So the probability, you can all go into Brave thinking, oh, I'm not so bad, huh? Right? So probability acts, so here's a question. What is the probability you go out into the population, randomly select someone, and that their IQ is greater than, let's say greater than or equal to 130? That's the question that we'll answer. What percentile, right, would this put us in? Or put you guys in? Right? And so the question, well, so if I wanted to compute that probability, I know I'd have to do this, right? I'd have to say, I'd have to calculate the definite integral from 130 off to infinity of this probability density function that's attached to the random variable. But I don't have a nice cumulative, I don't have a nice antiderivative function for my probability density function over there. Okay. So what we can do is we can transform this back to a standard normal random variable. Right? I could write it this way. I could say, well, greater than or equal to, let's just write it as 1 minus the probability x is less than 130. And then to transform it back to a standard normal, a z, right? I will take my x and I'll subtract off my mu, which is 100, and I'll divide by my sigma, which is the square root of 15 squared. It was 15. Okay. Which would be then, subtract off mean, divide by the standard deviation, 130 minus 100 divided by 15, which is 30 divided by 15, which is 2. Okay. So notice, let's just rewrite that. So if I can, what this is allowing me to do is to go back to what is called the standard normal random variable. Let me pull up, is it that one? Nope, I want, RStudio, I want this thing here. it allows me to go back to this table and just figure out, okay, what is the area to the left of 2 on this standard normal random variable table. And I would look on the side here, a bunch of negatives here. You can look at this later, but there's 2.0 is here, and then this column you follow to get the second decimal place. So we would want 2.00, and we get this value right here is going to tell me the area to the left of that, and it's 0.9772. Should have been a minus there, right? So it would be 1 minus, and I can look up on the one table, 0.9772, which is let's see if I can do any arithmetic here, 228. I'm sorry, 0.0228. Okay. So 2% of the area, 0.0228 of the areas to the right, 0.9772 is to the left. Okay. That means that the probability of just going out into the population and doing an IQ test on someone, if you believe such things work and tell you anything, would be, you would only find, there'd only be about a 2%, a little better than 2% chance to find someone with an IQ that was, at that point, greater than or equal to 130. Okay. So that would be the calculation there. We can go back to, let's see here, let's go over to R, right? By the way, we don't need tables anyway. At this point, we don't really need tables. We could use R, right? Because we could go here with, here's my random, right? I could just do a, here's the probability density function that would describe IQ, right? There's a picture of the normal random variable. Notice the mu is equal to 100, and that's where the max of the bell curve is. The sigma squared is equal to 15 squared, and the sigma is equal to 15, which is telling us something about the spread of that thing. And here's what I could do, right? Just some of the commands we have. R norm takes a random sample, so I'll just take a random sample of size 100. Pretend like I went out and just tested 100,000 people from this distribution. At random, right? Tried to make everything as independent as possible. And then I take the histogram of that. It should look like a probability density function, and it certainly does look like it. I mean, I see some spots where things look a little higher than they should, and maybe a little lower, but on average, it sort of smooths out to what I would expect it to. Right, that's the probabilistic nature of doing a sample. It won't be exactly, but the larger my sample, the more it should really look like what I expect it to look like. Okay. So one way to answer this question, what's the probability I select someone at random, and and in this case their IQ is greater than or equal to 130. One way I could answer that is I could go out and sample 100,000 people. I could get an estimation on it, and I could just count how many are greater than 130. Right? And out of that 100,000, there were 2,352, right? Which is about 2.3, 2.4%, right? Which is pretty close to this one right here, right? Again, I expect it to be in the ballpark. I don't expect it to be exactly the same, right? And what we did there is we just added up all of the results that were out here on the tail of my normal distribution. Okay? And that's how many there were. I can answer it exactly. Remember, P norm will give me the cumulative distribution function for a normal random variable. So P norm 130, 115. By the way, I had mentioned this difference between sigma and sigma squared. R uses sigma here. Okay. And R is more focused on statistics type things than probability type things. So they use a sigma there. So I'm not plugging in 15 squared here, I'm plugging in 15 because that's how R thinks about the normal random variable, as a mu and a sigma, not a mu and a sigma squared. But our book and everything we're going to do is going to focus on a sigma squared. So just know that difference. Okay. So this should give me the area to the left of 130, and I take 1 minus it, and it will give me the area to the right of 130. And I get that value, 0.2275 Yeah, which is close. I'm not going to worry about the difference in the actual particular values there. 0.2275. I think I looked. 2275. Was that right? 2275. Yeah, 228. Yeah. No, I'm sorry. If I round 2275 to 228, yeah, that would work. So I get the same value, or at least the same value. This gave me out to 3 decimal places, 4 decimal places. And again, what we did there is we just computed the area, or we let R compute the area to the right of 130 for us. Okay. So another question, right, a related question would be the claim is the average college graduate has an IQ of 114. And so we could ask that same question. Well, what's the probability we just go out into the general population and start testing people, and we find someone with an IQ of at least 114, right? And so again, what would we do? It would be 1 minus the probability x is less than or equal to 114. Notice I'm playing pretty fast and loose with less than or equal to's and less than or, you know, if I want it. It's because when I'm dealing with continuous random variables, there is 0 probability at any point. So it doesn't really make a difference if I put greater than or equal to or less than or equal, you know, or greater than, for instance, because the endpoint doesn't have any probability attached to it. That is not true with discrete random variables where all the probabilities are at points. So with discrete random variables like geometric and binomial, we have to be very careful about the inequalities. With a continuous, we don't really have to be so careful. But don't get lazy with the one and make it lazy with the other one too. So this probability, which would equal 1 minus c, and then I get the z by subtracting off 100 and dividing by 114 minus 100 divided by 15, which would be 14 over 15. Okay. And if I remember, 14 over 15 would be like 1 minus the probability z is less than, I think it was 0.933, something like that. Okay. And so again, we could put this back into the table, or we could look at our table over here and 0.90, and if I want to go over to 3, would be over here, and it's so fuzzy I can hardly see it, but I think it's a 0.8238, or something like that. Which would be 1 minus, which would be, what is that, 0.1762, I'm tiring myself out now, right? Right, which would tell me the probability I could go out into the population and find, just test people at random, test a person at random, and their IQ would be greater than or equal to 114, would be about, you know, it happened about 17.6%. So I just say, this process of, notice what we're doing on the right-hand side is we're taking the value that we're interested in, right, and we're subtracting the mu and we're dividing by the sigma, right? When we do that, that's oftentimes called the z-score. If you've had some statistics courses at some point, or, you know, some things that, you know, claim to be statistics courses, right, that the z-score is when you take your value, when you're dealing with, especially with normal random variables, and you subtract off the mean and you divide by the standard deviation, right? Because that z-score relates everything back to the standard normal random variable. So we can figure out probabilities by finding the areas on this one particular curve, and so we only need one table to do that. All right, 5 minutes. There's a couple of other things that are nice about that. Let's see which. Okay. So we could go over. Oh, yeah, I do run R, so we're good here. All right. So again, the rest of this is just the same thing. Let me just point out here. Okay. So here's an example of our standard normal random variable as R draws that picture for us. Here's a cumulative distribution function for R. We do not have a nice functional relationship for it. It's just the area to the left of the curve. Let's go back to the probability density function. Okay, so there's our standard normal probability density function. And so there's certain questions that we're oftentimes interested in, or it's good to know with normal random variables. Okay. So for instance, I put those two red lines at, for the standard normal at 1 and -1, which means, let's see, under my z-score, would be the question of, I could ask the question, what's the probability that's between those two red lines? Which is, what's the probability that, something's going to end up within one standard deviation, which is within one square root of variance of my parameters. Okay. So in this case, it would be saying, what's the probability that if I test someone at random, that they would have an IQ between 100 plus 15 and 100 minus 15, so between 85 and 115. Right? So by computing the area under the curve there, that would give me that probability. Oh, and the answer was 68.2 or 68.3, right? 0.682. Okay. So about 68% of the probability, likelihood, is within one standard deviation, right? It's telling us approximately 68% of the population would be in this range of 85 to 115 in terms of an IQ. Right? Or, I'll put another set of lines there, at 2 standard deviations. Okay. Right? So this would be like saying, okay, well, what percentage of the population would be, according to this, between two copies of 15, so 30, so between 70 and 130. Right? And so then I could go back to the standard normal random variable, and I could calculate the area under the curve, or I could have, I could look up off the table, or I could have R do it for me. Okay? And again, it's just the cumulative distribution function for the standard normal random variable at 2, minus the same thing at -2. And the answer is about 95.4, right? So 95.44, 4 or 5% of the probabilities within 2 standard deviations, 95.45, percent of people would be between 70 and 130. Meaning that you would then have, about 4.5% of the population outside of that range. And you would expect half above and half below, given the symmetric nature of all of it. And then you could go one more, 3 standard deviations, right? The green ones are pretty light there. And if you're within 3 standard deviations, you now have, 99.7% of the probability, right, is within 3 standard deviations, which on the one side up here would be 55, seems pretty low, and on the other end, it would be 145, which is pretty high, right? And so you would have something like 0.003 probability of being outside of that, or actually something close to 0.3%. 0.3% of the population would be outside of that. Again, about half below and half above, if you believe in normal distribution of all of this. Okay. So we're interested in these things with standard normal. What percentage is, what's the likelihood of ending up near the mean is the question, right? Near the average value. And we have this about 68, 95, 99.7% chance of being within 1 standard deviation, 2 standard deviations, 3 standard deviations are things that are oftentimes worked with. So just keep that in mind as we go forward. And those are some of those things. And again, what we can say in terms of, this is the nice thing about this transformation, what we did at the beginning of class is, what I can say about the standard normal has the exact same or equivalent interpretation for every other normal random variable. Instead of using 0s and 1s, we're just using our other mu's and our other sigmas. Essentially, we're taking and producing a z-score, and once we produce that z-score, every statement is exactly the same in the sense of, what's the probability the z-score is going to be in this range, and this range, which you also get the other interpretation. Okay, so I think we did enough for me to throw a couple of homework questions at you in terms of computing some probabilities. You get a little practice. I'll give you a couple questions. You get a little practice using a table of values. Appendix B from our textbook has a sharper version of that table of values. That's just a scanned-in version from something else. But anyway, I'll give you, I didn't give you any homework. I thought your quiz was probably enough on Monday. I'll give you a couple of homework questions, and then, this is pretty much where then the exam for next Wednesday will end. There could be some questions with normal random variables, mostly just the probabilistic nature. Z-scores, maybe using a table. Okay, so we will stop there.